Come on, my dears, let us begin with the last chapter in the syllabus now, chapter number 8 about waves. My dears, this chapter is bit long, very important from understanding point of view. For further understanding of the subject, it is an essential chapter, and from examination point of view also it is very important. Okay, and we will study each and every article very much in detail. I just urge everybody to pay very nice attention on the screen. Okay, fine. First of all, before we study about what is called wave, let me realize you about importance of study of waves. Perhaps in the all branches of science, among all the topics, if any topic is of utmost importance, extremely important, having maximum importance, it is this topic about waves. Why it is so much important? I can make you convinced for that. Look, first point about sunlight. If you discard sun from the universe, if you remove sun from the universe, then tell me, can we survive? No. No living being can survive in the absence of sun. Why? I am showing you the reason for that. In the absence of sun, you will not have sunlight. And in the absence of sunlight, the plants, the green life cannot undergo the process of photosynthesis, and hence they cannot release any oxygen. And if there is no oxygen in the atmosphere, tell me, can we survive? We cannot. So at present we are surviving because of presence of oxygen, but that oxygen is delivered into the atmosphere by the green life, and that is through the process called photosynthesis, which is possible only in the presence of sunlight. That is, we require sun. Okay, and let me tell you, my dears, this sunlight reaches to us in the form of waves, correct? So the credit of receiving of sunlight goes to waves. Okay, fine. Then we go for visible light. Almighty has created this beautiful world, and just to see that world, Almighty has donated eyes to all living beings. But then tell me, can we human beings, can we see anything in the absence of visible light? No, we cannot see. We are blind for other lights other than visible light, correct? So only in the presence of visible light, things are made visible to all human beings. So we can see the thing in the presence of visible light, and that visible light also propagates in the form of waves, correct? Fine. Third, about sound. At present I am speaking and you are listening, correct? But then that process, that communication is established because of propagation of sound waves in the medium of air, and that sound energy also propagates in the form of waves. Then you will study in third semester that tiny materialistic particles in a state of motion behave as if they are waves. In the entire universe, you will find only two entities. One is matter, another is radiation. Radiation already has wave nature, but the tiny materialistic particles in a state of motion behave as if they are waves. Such waves are called matter waves. They also are waves. And last point, my dears, about modern communication. At present, over the entire globe of earth, any person located anywhere is in a position to contact any other person immediately. Such a fast, such an accurate communication is possible because of transmission, propagation and reception of radio waves, which is a part of electromagnetic waves, again they are waves. So now tell me, our life is grateful to waves. Existence of our life is grateful to waves. Then watching anything is grateful to waves. Hearing is grateful to waves. The one entity of entire universe is behaving like waves, and the modern communication is established through waves. Now you must have realized the importance of study of waves. And among all these points, what is most important point for you, for the students, because it is in the syllabus, from examination point of view also it is very, very important. Okay. So now I think you are satisfied, you are convinced with the introduction of this chapter. Now we should proceed in the chapter. Let me explain you what is called wave. It will take time not less than 40 minutes. Be very patient and be very passionate to understand about what is called waves. I am showing you. To understand about what is called wave, you please consider one-dimensional elastic medium. One-dimensional elastic medium. For example, a string which is stretched and kept under proper tension is an example of one-dimensional elastic medium. How? I am showing you. If you consider a string which is very thin, stretched and kept under proper tension, then its all constituent particles are arranged along a straight line. That's why we call it one-dimensional medium. Moreover, if you produce some disturbance in that string which is stretched and kept under proper tension, if you produce some disturbance, then after some time if you stop producing disturbance, you will notice when you are producing disturbance, at the time some sort of shape is produced in the medium, and that shape diminishes gradually, and after some time the string assumes its original condition. Property of a body to restore its original condition is the property of elasticity, and because such a string has that property, we can call that medium as elastic medium. Correct? So a string which is kept under proper tension and stretched is an example of one-dimensional elastic medium. Such a string you please consider over here, whose one end is tied with a wall or with a rigid support, and another end we just keep in our hand. Fine. Now see what I am doing now. Hold this end in your hand. Okay, fine. And then you just displace it slightly from equilibrium position. Process of displacing any constituent particle of a medium from its equilibrium position is known as disturbance, is known as producing disturbance. So what are you doing here? By displacing this particle, what are you doing? You are producing disturbance in this medium. Correct? But don't produce the disturbance haphazardly. No. Produce the disturbance the way I am showing you. Look, hold that end of the string this way, and then you just move it this way. Correct? Make the first particle oscillating this way. That is, it should perform periodic motion on a straight path about its fixed point. And when periodic motion is performed on a straight path about the fixed point, we call it oscillatory motion. Correct? And during that oscillatory motion, if a force exerted on this particle is directly proportional to its displacement and opposite to displacement, then that motion is called simple harmonic motion. So this particle will start now performing simple harmonic motion. And don't you know, any particle performing SHM is called SHO, simple harmonic oscillator. So now this will act like a simple harmonic oscillator. Fine. And for simple harmonic oscillator, don't you know the equation of displacement? Equation of displacement is this: y equals to, look, a sine omega t plus 5. Let me rewrite properly. Look, y equals to a sine omega t plus 5. Fine. And now just give me identification of each symbol. Come on. Y is displacement at the end of t time. And then what about capital A? It is amplitude of SHM. What about omega? Angular frequency of SHO. T is given time and phi is initial phase. Wait. What are you doing here? You are displacing this particle from its equilibrium position. And then after first you are allowing it to move towards positive end of the path. You know, whenever SHO starts its motion from fixed point, and firstly if it is going towards positive end of the path, then initial phase is to be taken 0. So right now phi is 0. Phi is 0. Correct? Fine. And now when phi is 0, just put it here. So come on, y equals to a sin omega t. Y equals to a sin omega t. Correct? What is omega? Angular frequency. In terms of periodic time, don't you know its formula? Omega equals to 2 pi by capital T. Omega equals to 2 pi by capital T. Tell me, what is this capital T? Periodic time. Periodic time means what? Time taken by particle to complete one oscillation. Now time taken by that particle to complete one oscillation is periodic time, that is capital T. You just do one thing, you divide capital T into 8 equal intervals of time, and then each equal interval will be T by 8, correct? As such, you can have any number of parts of capital T, any number of equal parts of capital T, but we go according to textbook. In textbook they have divided capital T by 8. So each equal time interval would be capital T by 8. Then here I am writing different instants of time. Look, first instant of time I am going to take t equal to 0, then t by 8. Then add t by 8 with t by 8, it will be 2t by 8. Plus t by 8 will be 3t by 8. Plus t by 8, 4t by 8, 5t by 8, 6t by 8, 7t by 8, 8t by 8, that is capital T. Correct? And as time passes on, what will happen to the position of this particle? Where would be its position? What would be its displacement? We can find out from this formula. All these values of small t, you can put it here, then turn by turn you can find out this displacement, and all those displacement values are coming out respectively. Look here, 0, a by root 2, a by root 2, 0, minus a by root 2, minus a by root 2, 0. Then you will have one question that how these values are obtained. Okay, I am showing you one example. Out of these values of small t, you can just choose any value and you can put it here. You can calculate using this formula, you can find out value of y. How I am showing you. Just for example, you take at t equal to 7t by 8. T equals to 7t by 8. Just put it here. Put it here. I should get displacement how much? Minus a by root 2. Correct? Let us check whether we are getting or not. Come on, put small t equal to 7t by 8. Small t equals to, look here, 7t upon 8. Correct? Rest of the values as it is. And now tell me, tt will cancel. 2 4s are 8. So now it is 7 pi by 4. 7 pi by 4. Correct? Now tell me, a as it is. Sine of 7 pi by 4. 7 pi by 4 means what? 2 pi minus pi by 4. Isn't it? And 2 pi minus pi by 4 means what? Fourth quadrant. In fourth quadrant, sine function is negative. Sine function is negative. Moreover, because it is 2 pi, it is as good as 4 into pi by 2. 4 into pi by 2. 4 into pi by 2 means the coefficient of pi by 2 is 4, which is even number. So sine will remain sine. Sine will remain sine. Okay. So sine of 2 pi minus pi by 4 is nothing but minus sine pi by 4. A as it is, minus as it is. Don't you know value of sine of pi by 4? It is 1 by root 2. And then when it is multiplied with minus a, it will become minus a by root 2. Minus a by root 2. Correct? Fine. So y equals to minus a by root 2. Look here. Y equals to minus a by root 2. So the way at this very instant we have got this value of y. Similarly, at other instants of time, if you put it here one by one, you will get values of y as per this table. Okay. Now I want you to remember these values in the same order without any mistake. Look here now. First of all, you take 0 position, correct? Path of SHO is right now vertical path. then this is 0, then this is a by root 2, say this is a by root 2, 0, minus a by root 2, minus a by root 2, 0. How are these values in the diagram? I am showing you. Look, path followed by SHO is a straight path, let it be this path, okay. For this straight path, tell me, this is the midpoint or equilibrium position or fixed point y equal to 0, correct. Maximum displacement on either side of fixed point is called amplitude. The upper end point of the path or positive end of the path is y equals to plus a, correct. At negative end of the path or at the lowest end of the path, y equals to minus a, fine. If this much is amplitude a, then this much is a by root 2. A by root 2 means a into 1 by root 2. 1 by root 2 is 0.7071. 0.7071. If you multiply by 100, you will get the value in percentage. It is approximately 70% of amplitude. 70% of amplitude. So if this much is amplitude, then this much length is 70% of that total length. Okay, 70% of this amplitude comes out to be this much, and it is a by root 2. The way you have shown the position y equal to plus a by root 2 on the upper side of this fixed point, similarly with the same distance on lower side, you can write here y equals to minus a by root 2, correct. Now if you want to remember all these values in the same order, I suggest you one idea for that. You simply move this way, look here this way, correct, then come down, go at the lowest end and then come up, that's all. At the end of one round trip, wherever the sign of arrow is placed, you just take a pause and you speak the corresponding value of y. You will get all those values respectively in the same order. Just check it, starting from 0, correct. Is it the first value 0? Yes. Then go from here to here. What is the value of y? A by root 2. Come on, check it, a by root 2. Then a, correct. Then come down, here it is a by root 2. Come down, here it is 0, here it is. Go down, it is minus a by root 2, here it is minus a by root 2. Still go down, it is minus a, here it is. Then come up, come on, here it is minus a by root 2. And then when you come from here to here, again y value is 0, correct. So how is the change in the value of y during the oscillation? I am showing you, look, 0, a by root 2, a by root 2, 0, minus a by root 2, minus a by root 2, 0. Simple. Last time, 0, a by root 2, a by root 2, 0, minus a by root 2, minus a by root 2, 0. Got it? Fine. Now, to understand about what is called wave, you please consider a extremely thin string which is stretched and kept under proper tension. Suppose that string is this, look here, that string is this, okay, fine. You can take any length, okay, I have shown this much length, fine. Now on this string, I just consider 9 particles. Out of innumerable particles, I just consider only 9 particles. Come on, those 9 particles are such that distance between each 2 consecutive particles is same, and they are A, B, C, D, E, F, G, H and I. Okay, fine. Now at time t equal to 0, all these particles are at their respective equilibrium positions, that is at y equal to 0. Okay. Now how to draw this figure? I am showing you. I have taken special pain to draw this figure. I just appeal everybody to understand this whole phenomenon very nicely, please. How to draw this figure? First of all, you draw 9 vertical lines. 9 vertical lines parallel to each other. Not only that, distance between each 2 consecutive lines must be same. Perpendicular distance between each 2 consecutive parallel lines must be same throughout this diagram. Okay, fine. And then after, you prepare 9 horizontal blocks like this. Say this is first block, this is second block, this third block, like that up to 9 blocks. Okay. And these are the figures showing you successive progression in the diagram. At times t equal to 0, t by 8, 2t by 8, 3t by 8, 4t by 8, 5t by 8, 6t by 8, 7t by 8 and 8t by 8, that is capital T. Okay. Let us take all these figures one by one. Say for this particular diagram, this central position is y equal to 0, top end is the positive end of the path, it is y equal to plus a, the bottom end is lowest or negative end of the path, that is y equals to minus a, and somewhere here it is a 70% of this amplitude, let it be y equals to plus a by root 2, on the lower side it is y equals to minus a by root 2, correct? Similarly, you speak out all these values for this block suppose. Come on, for this block, how much is this? What is this position? Y equal to 0. Come on, this one is a by root 2. This one is a. Come on, a by root 2, 0. Here it is minus a by root 2. Minus a by root 2, 0. Come on, speak out for this block. 0. Come on, a by root 2, a by root 2, 0. Minus a by root 2, minus a by root 2, 0. Correct? Say for this one, come on, 0. A by root 2, a by root 2, 0, minus a by root 2, minus a by root 2, 0. Got it? Fine. At time t equal to 0, all the particles are at their respective equilibrium positions. And what we do now, at time t equal to 0, we start producing disturbance of simple harmonic type in the very first particle, say particle A, correct? And when that particle will start performing SHM, we will call it SHO, simple harmonic oscillator. And for simple harmonic oscillator, don't you know, at this many instants of time, the values of displacement will be this many, okay? Throughout the discussion, we will follow this table, okay? Now tell me, if you allow t by 8 time to get lapse, then at the end of t by 8 time, the particle which was earlier at y equal to 0 will get displaced and will come at the position a by root 2, correct? At the end of t by time, what is the value of y? A by root 2. So this particle will simply jump from 0 to a by root 2. Look here, from 0 to a by root 2. That is the first jump. Jump number 1 is from 0 to a by root 2. Look, from 0 to a by root 2, correct? But that thing you have to show in the second figure, because second figure is for t by 8. So in this second figure, you must show this particle being displaced from 0 to a by root 2 here, correct? And at that very instant of time, t by 8, it so happens that that disturbance is coming at second particle, that is particle B. At that very instant, this particle B is on the verge of getting displaced. It is about to get displaced, but yet it has not displaced, okay? And for the rest particles after particle B, because they have not received any disturbance, still they are at the rest positions only. Still they are at their respective equilibrium positions. Fine. So that displacement would be 0, 0, 0 like that, correct? You please join the consecutive particles, A with B, B with C, C with D, and then you will get the shape produced in the string. Shape produced in the string will be like this. Fine. At which instant time? At instant t by 8. Allow another t by 8 time interval to get lapse. T by 8 plus t by 8. Now the time is 2t by 8. Correct? At time 2t by 8, tell me the value of y is a. That is, the particle which was earlier here now will jump from here to here. It is its second jump. It will jump from a by root 2 to a. So now this particle will jump from here to here, correct? It will jump from a by root 2 to a, it will come at the top end. And here this particle got the disturbance at t by 8, and after that you have allowed another t by 8 time to get lapse. After the particle receives the disturbance, and then after if t by 8 time gets lapse, then it will simply jump from 0 to a by root 2. So for this second particle, it is the turn for the first jump, and during first jump, it will so happen that particle will simply jump from 0 to a by root 2. Come on, from 0 to a by root 2. But that thing you have to show in the third diagram. Come on, 0 to a by root 2, correct? And exactly at this much time, this particle C simply receives the disturbance. Exactly at that moment, this particle C is about to get displaced, but yet it has not been displaced. So its position is y equal to 0, and then after subsequent particles also remain at the respective equilibrium positions. Correct? Fine. Join the consecutive particles. What do you get? String? No, string though we had already. String though we had already, you will not get the string. String though we had, you will get the shape produced in the string. When you join A with B, B with C, C with D, like that, you will get the shape produced in the string. That shape is like this at time 2t by 8. Allow another t by 8 time to get lapsed. So 2t by 8 plus t by 8, it will be 3t by 8. Correct? Look here. At 3t by 8 is going to, what is going to happen? The particle which was earlier at A now will jump from A to A by root 2. Come on, now it is third jump. Already particle was here, and when it is undergoing third jump, it will be jumping from here to here, from A to A by root 2. From A to A by root 2. So this particle will come down from A to A by root 2. Look here. Correct? This particle will jump at the highest position, that is plus A. This particle will jump for the first time, that is A by root 2. Look here, A by root 2. And the disturbance comes here at the end of 3t by 8 time. Correct? At this very moment, this particle is about to get displaced, but yet it has not been displaced. And for the subsequent particles, still their positions are equilibrium positions only. So y equals to 0. Fine. Now allow t by 8 time to get lapsed additionally. Then 3t by 8 plus t by 8, it will be 4t by 8. Correct? Now tell me. Now you can just tell me. Come on. This particle already has started coming down, so it will jump from here to here. Correct? Come on. It will jump to, come on, 0. From A by root 2 to 0. Just go on checking with the next figure. Come on. A by root 2 to 0. This particle will come down at A by root 2. This will go up at A. This will jump for the first time at A by root 2. 0, 0, 0, 0, 0. Correct? Join the consecutive particles. You will get the shape produced in the string at time 4t by 8. The shape is like this. Correct? Fine. Allow another t by 8 time to get lapsed. 4t by 8 plus t by 8. It will be 5t by 8. And now this particle will jump from 0 to minus a by root 2. This particle comes down at minus a by root 2. This comes down at 0. This comes down at a by root 2. This goes up at a. This jumps for the first time at a by root 2, and here this particle is about to get displaced at time 5t by 8, and subsequent particles are still equilibrium positions only, 0, 0, 0, 0. Correct? Join the consecutive particles, you will get the shape produced in the string. Then after at time 6t by 8, what will happen? This particle will come down at minus a, this will come down at minus a by root 2, this will come down at 0, this will come down at a by root 2, this will jump at the highest position, it will be plus a, this will jump for the first time, that is a by root 2, 0, 0, 0. Correct? Join the consecutive particles, you will get the shape produced in the string at time 6t by 8. Then after another additional t by 8 time gets lapsed, then 6t by 8 plus t by 8, that is 7t by 8. This particle will jump from minus a to minus a by root 2. Correct? This will come down at minus a, this will come down at minus a by root 2, this will come down at 0, this will come down at a by root 2, this will jump here, that is a, and this will jump for the first time, that is a by root 2, 0, 0. Correct? Come on. Now 7t by 8 plus t by 8, that is 8t by 8, which is capital T. At the end of capital T time, what will happen? This particle will jump from here to here, from minus a by root 2 to 0. Come on, from minus a by root 2 to 0, that is jump number 8. It's jumping from here to here, 0. This will go up at minus a by root 2. This will come down at minus a. This will come down at minus a by root 2. This will come down at 0. This will come down at a by root 2. This will go up at a. This will jump for the first time, a by root 2 and 0. Correct? Join the consecutive particles, you will get the shape produced in the string. In front of your eyes, all of you are witnesses. Very important physical phenomenon has taken place over here, and that phenomenon is only going to be called as propagation of wave. Actually, tell me what has happened here. Tell me. At time t equal to 0, you had simply produced disturbance of simple harmonic type in the very first particle, that is at one end of the string. At the end of t by time, that disturbance came at particle B, then after at C, D, E, F, G, H, I. So, after capital T time, it has reached the another end of the string. Now, tell me, in this string which is stretched and kept under proper tension, when you are producing disturbance in one end, that disturbance moves ahead, away from the source, away from that particle at which you are producing the disturbance. And when the disturbance is moving ahead, away from the source, what does it do? It simply displaces the particles coming in the way, either upwards or downwards, and the disturbance itself goes ahead and ahead. Such a movement of the disturbance, such a motion of disturbance is only known as wave, or we call it pulse. Is called wave or pulse. It is not necessary that for the propagation of this wave, for the motion of this disturbance, not necessary that medium must be present, not necessary. In semester 3, you will study about electromagnetic waves, which are the waves which can propagate even in vacuum also. And then their disturbance is also known as, motion of that disturbance is also known as wave. So, the most general definition of wave, you can give it this way: motion of disturbance might be either in medium, might be in vacuum, everywhere. Motion of disturbance is going to be called as wave. How will you define it? Very simple. Motion of disturbance either in medium or in vacuum is called wave. Is called wave, is called wave. Motion of disturbance either in medium or in vacuum is called wave. Is called wave, is called wave. In the whole definition, in the whole phrase, there are 4 groups. In each group, you will find 3 words. Look here. Motion of disturbance either in medium or in vacuum is called wave. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Correct? Motion of disturbance either in medium or in vacuum is called a wave. Is called a wave, is called a wave. My dears, now I appeal everybody to recite this whole definition along with me, and you will really enjoy. My all past students, they have remembered this definition. They might have studied this definition under me before some 25 years or so. Then also for such a long period of time, they have remembered this definition. And I just expect you also to remember it. Please, come on, join with me. Motion of disturbance either in medium or in vacuum is called a wave. Is called a wave, is called a wave. Come on. Let us now start singing this definition with proper rhythm this way. Motion of disturbance either in medium or in vacuum is called a wave. Is called a wave, 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 is called a wave. Is called a wave. Got it? Motion of disturbance either in medium or in vacuum is called a wave. Is called a wave, is called a wave. Will you please remember? Fine. Come on, my dears, now to understand this phenomenon better, let us take some other examples of propagation of wave. I am showing you one by one some other examples of phenomenon of wave propagation. First, in a solid medium, you please consider a iron rod, correct? An iron rod. Now this is a solid medium, and here we experience that if you strike hammer at this one of the two ends, and immediately after that when you touch at this second end, you will have some sensation of vibration at the other end. Now tell me, actually you are striking the hammer at this end, correct? then particles at that end are set into vibration, correct? Disturbance is produced in those particles. But now it so happens that this is becoming now source of production of disturbance, and now the disturbance moves ahead away from the source, and whichever particles of that medium come in the way are getting displaced either upward or downward or to and fro. In short, that disturbance is moving and displacing the constituent particles of that medium, and ultimately it reaches the other end of the medium, correct? So here also we have motion of disturbance from one end to another end. It is nothing but wave, but that wave is propagating in a solid medium, correct? Fine. Now let us consider that example of wave propagation which takes place in liquid medium, say water. You just consider this as calm surface of water, okay? Fine. Now you just place some spherical bob on the surface of water and you make it oscillating up and down, okay? When you make it oscillating up and down, ultimately what are you doing from physics point of view? You are producing disturbance here in the medium of water, and now that disturbance will start moving ahead away from the source. Source is this, now it will start moving ahead. Suppose it moves ahead in this direction, then the particles on the surface of water will be getting either displaced upwards or downwards. Those particles which are displaced upwards, because of that much part of water surface is lifted up. There is a bulging of the surface, and then the shape is produced which is called crest, okay? And because of the particles which are getting displaced downwards, that much part of the water surface is depressed downward, and because of that there is some sort of valley, some depth is there, correct? And because of such a curvature, we just call it trough. This one is called crest, which is bulge part. This one is depressed downwards, it is called trough. So this is crest, this is trough, correct? Come on, crest, trough, like that, okay? So I mean to say, when you oscillate this bob, come on up and down continuously, you will have continuous production of disturbance, and thereby continuous motion of disturbance, and thereby propagation of wave on the water surface, which we call water wave, correct? It is an example of wave propagation in a liquid medium, got it? Fine. Then in a gaseous medium, I am showing you, consider this as a tuning fork, and these are the limbs or arms of a tuning fork, and this is the handle, okay? Now you just strike this tuning fork with some rubber pad. When you strike it, this pronges or this arms will start vibrating, correct? When these pronges they start vibrating, it so happens when it vibrates say towards right hand side, then here in this region of air medium pressure is increased, and because of pressure is increased, the particles of air medium are coming closer. So in this region where you are having the particles moving closer to each other, then because of that here you are going to have more density, more pressure, and this region in which the density and pressure have been increased, in that region we say condensation has taken place. What? Condensation. That's why I am writing C. C for condensation, correct? At that very moment, in the neighboring region, you will find that region in which the pressure and density are low, where we say rarefaction has taken place. That's why I am putting symbol R. C for condensation, R for rarefaction, correct? Fine. So condensation and rarefaction are taking place. And this is the picture at a particular instant of time. After half of the periodic time, the positions are interchanged. At the place of condensation, you will have rarefaction. At the place of rarefaction, you will have condensation, like that. So what I mean to say, as long as the pronges are vibrating this way, what happens? The disturbance is continuously produced in the air medium, and that disturbance moves ahead away from the source. And during that motion, what happens? The air particles are oscillating to and fro this way, correct? And then such a motion of disturbance is only known as wave. But because some sort of sound is heard during the propagation of this disturbance, we call these waves as sound waves, correct? Because some sound is heard, that's why. Okay. So this is the propagation of wave in an air medium, that is in a gaseous medium. Fine. Now you consider a queue in which some persons are standing. Okay. So a queue of persons. When some persons are standing in a queue, and if some other person is coming from behind at one of the end of the queue and is just pushing the next person, then what will happen? The next person will lean forward, correct? But again, to maintain the balance, he will come back to the original equilibrium condition, correct? But then as he leans forward, he passes on the disturbance to the next person, correct? So next person also will lean forward, he will also come back to his original position, and thereby he passes the disturbance on the third person, and so on. So this is how disturbance which is produced at one end moves ahead in the medium which is made up of persons standing in a queue. This is also propagation of wave, correct? Then you talk about railway coaches. Railway coaches. When you have a queue of railway coaches, say a train, and when you join engine at one end, that we call first coach, to which that engine is joined, that first coach at the time of joining of this engine, that coach will vibrate, correct? Then that because of that vibration, that disturbance is produced, and that disturbance is going to now travel in the medium of railway coaches, correct? The disturbance is passed on to the second coach, it also vibrates, makes the third coach vibrating, then after fourth coach is vibrating, and so on, correct? So this is also motion of disturbance in a medium made up of railway coaches. It is also called wave. In short, anywhere if you find the disturbance is produced and that disturbance is moving ahead away from the source, that very phenomenon in physics, it is termed as wave. Motion of disturbance either in medium or in vacuum is called a wave, is called a wave, is called a wave. Will you please remember now? Please. Now, let us go ahead in the chapter. Let me introduce you some physical quantities which are to be referred often and often in this chapter. So, better you try to understand nicely and try to remember also. First definition is about wavelength of wave, shown by symbol lambda. It is some sort of distance. But what is it actually? I am showing you. Consider this as one-dimensional elastic medium, say an extremely thin string stretched and kept under proper tension. Suppose I produce disturbance of simple harmonic type in this very first particle at time t equal to 0. And then at the end of capital T time, when this particle completes one oscillation, its phase will become 2 pi radian. How? Don't you know formula of theta in terms of number of oscillations? Theta equals to phi plus 2 pi n, phi plus 2 pi n. And because this particle started its motion from fixed point, firstly it went to positive end of the path, its initial phase is 0, plus 2 pi into n, where n is number of oscillations. At the end of capital T time, only one oscillation will get finished. So 5 plus 2 pi n, phi is 0, n is 1. So you will get total phase come on 2 pi radian. At the end of capital T time, phase of particle A has become 2 pi radian. But exactly at that capital T time, you can see at time t equal to t, the disturbance had just arrived here. So at that very moment, this particle had not started oscillating, so its phase will remain 0. Its phase will remain 0, correct? And at the end of capital T time, what was the shape produced in the medium? Look here, this sort of shape is produced, where this is trough and this is crest. Come on, this is trough and this is crest, correct? Now tell me, at the end of capital T time, phase of this particle is 2 pi radian, phase of this particle is 0. So if somebody is asking you, what is the phase difference between these two particles? Then it is 2 pi minus 0, that is 2 pi radian, 2 pi radian. It is phase difference, correct? And now you simply find out the distance between these two particles which have phase difference of 2 pi radian at any one instant of time, then that very distance itself is known as wavelength. wavelength shown by symbol lambda. Correct? Now tell me, how would you define wavelength of a wave? Very simple. Along the direction of propagation of wave, comma, the distance between two consecutive particles having phase difference of 2 pi radian at any one instant of time is called wavelength of wave shown by symbol lambda. Simple. Along the direction of propagation of wave, comma, the distance between two consecutive particles having phase difference of 2 pi radian at any one instant of time is called wavelength of wave shown by symbol lambda. Last time. Along the direction of propagation of wave, comma, the distance between two consecutive particles having phase difference of 2 pi radian at any one instant of time is called wavelength shown by symbol lambda. Simple? Fine. Then we go for what is called amplitude of wave, what is called periodic time of wave, what is called frequency of wave, and what is called angular frequency of wave. For these four quantities, the symbols are as per the previous chapter. Very simple. I am showing you what is that. When the wave is propagating in this string, what happens? Its constituent particles start oscillating about their equilibrium positions. They start performing simple harmonic motion. Say, if you are talking about this particular particle, say particle G, then at time 7t/8, at time capital T, it is at the highest position, and you can see the maximum displacement on either side of fixed point. It is called amplitude. So during the simple harmonic motion performed by this particle, its amplitude is this much, correct, which is capital A. But that is amplitude of oscillation of that particle. Same is known as amplitude of oscillation of wave. Same is known as amplitude of wave. Whatever is amplitude of oscillation of particle, same is known as amplitude of wave. Then whatever time is taken by this particle to complete one oscillation, it is called periodic time of oscillation of that particle. Same is taken as periodic time of wave. Number of oscillations completed by this particle about its fixed point in unit time is called frequency. But that is frequency of that particle. With the same is taken as frequency of wave. And finally, frequency of oscillation of particle multiplied by 2 pi radian is called angular frequency of oscillation of that particle. Same is taken as angular frequency of wave. Whatever is of particle, same is taken of wave for these four quantities. Which four quantities? Amplitude, periodic time, frequency, angular frequency. Okay. Now start giving definitions one by one. It's very simple. During the propagation of wave, comma, the amplitude of oscillation of particle of a medium which takes part in the propagation of wave is called amplitude of wave. Come on. The amplitude of oscillation of particle taking part in the propagation of wave is called amplitude of wave. The periodic time of oscillation of particle taking part in the propagation of wave is called periodic time of wave. Frequency of oscillation of particle of medium is called frequency of wave, and angular frequency of oscillation of particle of medium taking part in the propagation of wave is called angular frequency of wave. Whatever is of particles, same is of wave for these four quantities: amplitude, periodic time, frequency, and angular frequency. Okay. Last time now. Amplitude of oscillation of particle taking part in the propagation of wave is called amplitude of wave, shown by symbol capital A. Periodic time of oscillation of particle of medium taking part in the propagation of wave is called periodic time of wave, shown by symbol capital D. Frequency of oscillation of particle of medium taking part in the propagation of wave is called frequency of wave, shown by symbol small f. And finally, angular frequency of oscillation of particle of medium taking part in the propagation of wave is called angular frequency of wave, shown by symbol omega. Simple? Fine. Then, what is called wave vector of a wave? What is called wave vector of a wave? Very simple, huh? Its a symbol is small k. Tell me, what is the distance between these two particles? Come on. Wavelength. that is lambda. So distance between these two particles is lambda. But what is corresponding phase difference? Phase difference between these two particles at time capital T at a given instant of time. What is the phase difference between them? It is 2 pi radian. Wait. For distance lambda, if the phase difference is 2 pi radian, then if the particles are separated by unit distance, then what could be the phase difference between them? Let us find out. This into this upon this. This into this means 2 pi upon lambda. So this ratio 2 pi upon lambda is going to give you phase difference between two particles which are separated by unit distance at a given instant of time. Then such a phase difference is known as wave vector of the wave, shown by symbol small k. So what is the formula? K equals to 2 pi upon lambda. Here it is. K equals to 2 pi upon lambda. Correct? Define it. Along the direction of propagation of wave, comma, the phase difference between two particles separated by unit distance at a given instant of time is called wave vector of that wave, shown by symbol small k. I repeat. Along the direction of propagation of wave, comma, the phase difference between two particles separated by unit distance at any instant of time is called wave vector of that wave, shown by symbol k, small k. Its formula is k equals to 2 pi upon lambda. Simple? Fine. Come on, what about unit of k? Unit of k is nothing but unit of angle upon distance. Unit of angle upon distance. Unit of angle, SI unit, it is radian, and for distance it is meter. So unit of wave vector is radian upon meter. Simple? What about direction of wave vector? Direction of wave vector is taken in the direction of propagation of wave. If wave propagates along say positive x-axis, then you may write its wave vector like this. Vector k equals to, don't you know, vector equals to magnitude multiplied by unit vector. Correct? Magnitude is 2 pi upon lambda. Magnitude is 2 pi upon lambda, and along the direction of propagation of wave, we are supposed to take the direction of wave vector. Then, because it is right now positive x-axis, unit vector must be I hat. Correct? So vector k equals to 2 pi upon lambda into I hat. Correct? Last time, let me repeat the definition of wave vector. Along the direction of propagation of wave, comma, the phase difference between two particles separated by unit distance at a given instant of time is called wave vector of that wave, shown by symbol small k. Correct? Fine. What about wave velocity? Wave velocity. See, when the disturbance is produced here, it travels this much distance, say lambda, but at the end of how much time? In the time interval which is t minus 0. T minus 0 means capital T. So any wave will travel distance lambda in time called periodic time. Correct? And you know, distance travel in a definite direction per unit time is called velocity. So distance travel is lambda along the direction of propagation of wave, and the corresponding time in this capital T, that is periodic time. Come on, this lambda upon T will give you distance traveled by disturbance along the direction of propagation of wave in unit time. It is called wave velocity, shown by symbol small v. Distance traveled by disturbance along the direction of propagation of wave in unit time is called wave velocity, shown by symbol small v. But don't you know, 1 upon periodic time is nothing but frequency. So I am writing small f into lambda. Please remember this small formula, which is very useful in many of the numericals. You must remember v equals to f lambda. V equals to f lambda. Tell me in words. Wave velocity, this is frequency of wave. Lambda means wavelength of wave. Simple. Just multiply by 2 pi and divide by 2 pi. When you multiply by 2 pi, it is 2 pi f. 2 pi f into, when you divide by 2 pi, it is, come on, lambda upon 2 pi. Correct? Multiply f by 2 pi, so it is 2 pi f. Divide this lambda by 2 pi, so it is lambda upon 2 pi. Correct? Now tell me, frequency into 2 pi radian will give you angular frequency, that is omega. But if it is lambda upon 2 pi, and then it is reciprocal of k. So it is 1 by k. So this lambda upon 2 pi is nothing but 1 upon k. So when you multiply omega with 1 upon k, it will give you omega upon k. Simple. So please remember two formula for wave velocity. One is f lambda, another is omega upon k. Correct?